Welcome back to part 8 of upgrading my small lathe. Today we're going to look at mounting of the lathe, and I prepared a board here which I bolted the lathe down to, and I want to investigate the effects of a rigid mounting or a flexible mounting or something in between and see what suits me. I want to have a machine which I can move around from place to place without disturbing setups, so we're potentially looking at twisting the bed and the effect of the mounting on that, because a rigid option is almost certainly going to involve steel fabrication, and I don't have any welding plant, so that option is not so attractive for me. The first thing that comes to mind, of course, is if I bolt the lathe directly to this, then if the worktop surface moves in any way due to change in humidity or even the way it sits on the bench, then is that going to affect the alignment of the lathe? This is a very small machine. Now, scale is important. Actually, the bigger the lathe, the more difficult alignment is. And with smaller lathes, even when they're mounted rigidly, I suspect that alignment is not going to be such much of an issue. But I'd like to quantify it. And so to do that, I've mounted the DTI on the lathe, and I'm going to take some measurements. So we'll have a closer look and see what we discover. The base material I'm using is kitchen work surface, and it is 30 millimeters thick, or approximately 1 1/8 inches, made of chipboard with a surface on top there. At the moment the lathe is bolted down, 3 points at the headstock with 1/4 inch bolts, and 2 at the tailstock across the diagonal there. And what we're going to do is twist the base and see what effect that has on accuracy as measured here in the test bar, both in the horizontal and the vertical planes. So the way that I'm proposing checking the stability of the base and whether the base is distorting the lathe is to put a test bar in the mandrel using the Morse taper and extending it out as far as possible, and then checking movement on the end, both in the vertical plane and the horizontal. And to do that, I've made this test bar from a piece of silver steel or drill rod, and it has a 0 Morse taper on the end here, which I've just turned up on my other lathe, and that's a good fit in here. That will enable us to check deflection some 6 or 7 inches from the headstock bearing. So I'm placing the DTI on the back of the saddle, but we'll check the horizontal deflection as far from the headstock bearings as possible. So first of all, we'll put the load across this diagonal. So I'm going to lift this corner, and then we'll see what deflection there is. The weight is across one diagonal, and we have a deflection there of, I'd say, barely 1/4 thou. The same thing across these two corners. We have a deflection there of around about 1/2 thou. So that's a total deflection of 3/4 thou, and of course that would represent 1.5 thou off the diameter. Now we'll do the same test, measuring deflection in the vertical plane. The top left-hand corner and the bottom right-hand corner, I can't see any movement there, and the other diagonal, again, I can detect nothing. It's not deflection in the vertical plane that's the problem, it's the horizontal or lateral deflection which is an issue. And that makes sense, because twist in the bed is going to affect this measurement, not the vertical. Let's take a closer look at what's happening to the bed as we twist it. Here you see the datum, which is under the headstock, and that's nicely bolted down to our board. And then we also have the tailstock bolted down to the board, so as we twist the board, we're effectively twisting the bed. But what I should have taken into account is the position of the saddle in all of this. And you can see that here. So the twist that we're measuring is from this point. We get a clearer view of this if we look from above. You can see the headstock with its center line, and the test bar, which effectively is tied to our datum. Then we have the DTI at the end of the test bar, where it should be. But what is significant is where the base is mounted, and it's mounted at this position. Looking from the front, you can see the relative distances. Here's the headstock centerline, the saddle, and the DTI. And you can see from this that the saddle is less than halfway along the test bar. And that means that I am not actually taking a sensitive reading after all. We're only actually measuring the twist of the bed at that position of the saddle. What I should have done is move the saddle right up to the position where the DTI is measuring, and that would have given us a more sensitive reading. The reason I didn't do that was because the geometry of my stand didn't allow me to do that. I should have found another way of mounting the stand. Well, someone might say, why not put the stand on the square section of the bed towards the rear? I did think of that at the time, but what I really wanted to do was measure the twist across both the front and the rear sections of the bed. And to do that, you really need to measure off the saddle itself. So that's an explanation of why this measurement wasn't very sensitive. All this shows me that the twist in the bed is actually very significant, and is something I need to take into account in the mounting of this little lathe. Well, at last we can start actually talking about the design for mounting the lathe. So you can see here the lathe in plan with its front and end views, and also here the motor drive, which is more or less a self-contained unit. I've worked on the design of that, and I'll be sharing that with you in my next videos. Also at the back there is the power supply, but what is of interest now are the mounts at the headstock and the tailstock ends. So they have two plinths made from aluminium sheet, 10mm or 3/8 thick, and they fit under the headstock and the tailstock castings, which are machine surfaces. The headstock end sits on an approximated knife edge. I say approximated because it's not really a knife edge. It's that 3/8 material, radiused on the undersurface, and it has two holding down bolts at each end. So what that gives us is a mount which can ever so slightly rock to the right and left, but is stable in the fore and aft directions. At the tailstock end, we have a circular mount with a radius underneath, which approximates to a ball joint. And that enables the mount to rotate left and right, and also forward and aft. So in this way, we should be able to isolate any twist in the base from the lathe itself, and at the same time ensure that the lathe is stable. Whether we need some anti-vibration material in there, some rubber, I don't know, but we'll try with this, and then if we need to, we can add it later. In addition to that, we need to make the base stable, so we're going to have three legs with a position like this to give good weight distribution. But the idea here is that you can pick the whole thing up, move it around and put it onto another surface, hopefully without disturbing any settings on the lathe or upsetting any alignment. Well, I've already gone ahead and got the materials for the plinths, or the base. So this is the tailstock, this is the headstock plinth, they're different sizes. For the cross member, which sits underneath, I've decided to make that longer. Originally it was the same width as this plinth, but I've extended it just to give it a bit more lateral stability. And I also have a piece of material for the tailstock support. So I've already gone ahead and machined the tailstock plinth, so that's all squared up to size. I need to go ahead now and do the same for the headstock, and also start machining the cross member. So I'm just beveling the edges now of the feet on the cross member. Just putting a very shallow groove on the underside of the plinth to accept the cross member, and the reason for that is because this extruded section isn't actually flat, so I want to flatten it out and just provide a nice location for the cross member when it's bolted on. And I'm going to just take 1/10 thou off this. You can see indeed it's just cutting there in the middle. So I've set the dial to 0, so 1/10 thou is 1/4 millimeter. Okay, I've drilled pilot holes in the top plate or the plinth, and we're ready now to spot those through onto the cross member. As you can see, this fits nicely in that shallow groove there. So what I'm going to do is mount the cross member in my vise, and then we're going to spot through, tap one of the holes, put a countersunk screw in there, and then we can do the other two confidently. There was a slight burr on the other side of the holes there. I've just removed those, and now this seats nicely. We're opening up to the tapping drills for the 5mm thread. Well, I wanted a countersink for these socket head cap screws, but unfortunately I got the wrong size countersink. So I've just ground up an old drill to a 90-degree point, and we'll make do for that for the time being. I've already tested it works.
So it's time to start working on the tailstock plinth, and I'm marking out here the diameter of the recess to hold the little foot that sits in there.
Well, it's clear we're not going to finish this mount today, so let's just have a closer look at where we've got to, and then we can think about what's coming up next. The headstock plinth is ready for assembly. I transferred the positions of the holding down bolts from the base of the lathe using this transfer punch, which I made from a piece of silver steel, and that fits snugly into the machined holes in the base of the lathe and enable me to punch, or in some cases press, the point into this and then get accurately aligned holes. So I've drilled and tapped those. The cross member fits on nicely with our countersunk screws. The counterbores are not brilliant, but I explain the reason for that. They're functional, however. So this part of the assembly is almost complete, apart from the holding down bolt holes, which need to go in here. So we'll do those next time. The other plinth, I didn't show you the radius on the foot. I'm not sure you can see that clearly. Let's put a straight edge up against it. Maybe you can see it now. There's a radius there. I might need to make that radius come a little bit closer to the center so it's less likely to stick on the central position, so I might modify that later. So the foot locates in this slight recess in the other plinth, and that has a 6mm countersunk screw in there. And you can see here the punch holes which I reduced, so they're ready to be drilled and tapped. The next video we'll finish this off. We'll also cut the base to the right size, and I'll find some edging to put around this to make it a bit more durable. And also we'll be able to test it to see whether this kind of mounting has achieved what I was looking for. So a system where you can move the lathe around but maintain its accuracy. I'm going to be visiting Pakistan again in the next few weeks, so there'll be a pause on this series of videos on upgrading my small lathe. But I hope to do something from the other workshop, possibly based on the Colchester student lathe. So I hope you join me for that. Thank you.